In this lesson, we will examine the typical approach for dealing with two particles in quantum mechanics. Classically, the total energy for a two-particle system can be written as a sum of the kinetic energies of each particle and the potential energy of interaction between them. If we refer to the two particles as particle 1 and particle 2, then we can write the total energy, E, as the sum of the kinetic energy of particle 1, T1, the kinetic energy of particle 2, T2, and the potential energy of interaction between them, V12. In general, instead of thinking of the total kinetic energy as the sum of kinetic energies of the particles, it is more convenient to think of the total kinetic energy as a sum of translational and internal components. The translational energy can be thought of as the kinetic energy due to the overall motion of the two particles as tracked through their center of mass. And the internal energy is the kinetic energy due to motion of the particles relative to each other. Thus, internal energy is also referred to as the relative energy. The relative motion of the two particles can be described as vibration and rotation. The center of mass of two or more particles is a weighted average of their location. The weights we use for averaging are the masses of the particles. Consider a two-particle system. If particle 1 is located at coordinates x1, y1, z1, and particle 2 is located at coordinates x2, y2, z2, then the average of the x-coordinates is given by this expression. The x-coordinate of the center of mass, shown here as uppercase X, is equal to m1 times x1 plus m2 times x2 divided by the total mass. Here, m1 and m2 are the masses of particles 1 and 2, respectively. Uppercase M is the total mass, which is equal to m1 plus m2. The formulas for the y and z coordinates of the center of mass are similar. Simply replace x1 and x2 by y1 and y2, or by z1 and z2. Suppose we set up a coordinate system so that a proton is located at -1 nanometer and an electron is located at +1 nanometer. This means that, if we take negative locations as left of the origin, then the proton is 1 nanometer to the left of the origin and the electron is 1 nanometer to the right of the origin. Where is the center of mass of this two-particle system? The center of mass is the weighted average location of the two particles. Here's the formula for the x-coordinate of the center of mass. We multiply the location of each particle by its mass, add up the results, then divide by the total mass. If we plug in the location and mass of the proton and the location and mass of the electron, we get -0.9989 nanometers. This is essentially -1 nanometer, which is where the proton is located. We should expect this given that a proton is almost 2,000 times more massive than the electron. When one particle is so much more massive than another, the center of mass is essentially located at the heavier particle's location. Consider a diatomic hydrogen molecule. Suppose the nuclei are located at x equals 0 and 150 picometers. Where is the center of mass located? If we assume the mass of both nuclei are equal, then we expect the weighted average location to be exactly in between the two nuclei. The x-coordinate for the center of mass would be at 75 picometers. But what about the electrons? We can ignore them because their masses are very small compared to the nuclei. What if the atom at x equals 0 is protium, but the other one is a deuterium? Let's see. A deuterium nucleus consists of one proton and one neutron, whereas a protium nucleus consists of just one proton. Since the mass of a neutron is approximately equal to that of a proton, the mass of a deuterium nucleus is approximately twice that of a protium nucleus. So, we expect the weighted average location to be closer to the heavier isotope. If we were to do the calculations, we should find the x-coordinate of the center of mass to be at 100 picometers. Now, let's talk about internal or relative coordinates. If two particles are located at coordinates x1, y1, z1, and x2, y2, z2, then the internal x-coordinate, symbolized here by lowercase x, is defined as x2 minus x1. Likewise, the internal y and z coordinates are defined as the difference between the corresponding coordinates for particles 1 and 2. Think of the internal coordinates as where particle 2 would be located. if we were to set our origin where particle 1 is located. The internal coordinates tell us where particle 2 is relative to particle 1. Here's a simple example. Suppose the x-coordinate of particle 1 is 1 nanometer and that of particle 2 is -1 nanometer. Calculate the relative x-coordinate. The relative x-coordinate is just the location of particle 2 if we were to imagine moving the origin to where particle 1 is. It's calculated by subtracting x1 from x2. Since x2 is -1 nanometer and x1 is 1 nanometer, we get -2 nanometer. Recall that the total kinetic energy of two particles can be obtained by simply adding up the individual kinetic energies of the two particles. The total kinetic energy is just the kinetic energy of particle 1, shown here as T1, plus the kinetic energy of particle 2, shown here as T2. T1 is 1/2 times m1 times v1 squared, where m1 and v1 are the mass and speed of particle 1. T2 is 1/2 times m2 times v2 squared, where m2 and v2 are the mass and speed of particle 2. We can also get the total kinetic energy by adding up the translational and relative kinetic energies. The translational energy is 1/2 times mv squared. In this formula, we use the total mass, shown here as uppercase M, and the translational speed, shown here as uppercase V. Translational speed is the speed associated with the overall movement of the two particles as tracked through the movement of their center of mass. The relative kinetic energy is 1/2 times mu v squared. In this formula, we use the reduced mass, shown here as lowercase Greek letter mu, and the relative speed, shown here as lowercase v. From the definition of center of mass and relative coordinates, we can calculate the reduced mass, translational speed, and relative speed from m1, v1, m2, and v2. The translational speed is the speed of the overall movement of the two particles as tracked through their center of mass. We can calculate it if we know the individual masses and velocities of the two particles. First, let's define the x component of the translational velocity vector, shown here as uppercase V sub x. It's defined as the derivative of the center of mass x coordinate with respect to time. Plugging in the expression for the center of mass x coordinate, then factoring out the constants, we can show that V sub x for the center of mass is just the weighted average of the V sub x of the two particles, in much the same way that the center of mass coordinates are weighted averages of the individual coordinates. The same can be shown for the y and z components. In other words, the translational velocity is just the weighted vector sum of the individual velocity vectors, divided by the total mass. So, we can now easily calculate the translational speed, which is just the magnitude of the translational velocity vector. As with any vector, the magnitude of the translational velocity vector is just the square root of the sum of the squares of its components. Let's look at an example. Suppose a particle is moving at 8 meters per second to the right, while another particle, with 3 times the mass, is moving to the left at 4 meters per second. Let's calculate the translational speed for the two-particle system. First, we need to define which particle is particle 1. Let's say particle 1 is the particle that is moving to the right, and we'll take this as the positive x direction. We can write the velocity vector for particle 1, v sub 1, by listing its components v sub x1, v sub y1, and v sub z1. The component along the x-axis, v sub x1, is plus 8 meters per second, and the other components are 0. We are not given the mass of particle 1, so let's just call it m1. For particle 2, the velocity vector component along the x-axis, v sub x2, is -4 since it's moving to the left, and the other components are 0. We are also not given the mass of particle 2, so let's call it m2. Note that, in this problem, it is given that m2 is 3 times m1. The translational velocity vector is just equal to m1 times vector v1 plus m2 times vector v2 divided by the total mass. Substituting 3m1 for m2, we find that the translational velocity vector is 1/4 of the sum of v1 and 3 times v2. So, its x component is v sub x1 plus 3 times v sub x2 divided by 4, which turns out to be equal to -1. In the same manner, we can calculate the y and z components. In this case, both are 0. So, what does this mean? It means that the center of mass is moving to the left at a rate of 1 meter per second. To calculate the translational speed, we square each component, add them up, then take the square root, and we get 1 meter per second. The relative speed of two particles, the rate that the distance between them is changing, can be easily determined using vector components. First, let's define x component of the relative velocity vector, shown here as v sub x. It's defined as the derivative of internal coordinate x with respect to time. Since x is just x2 minus x1, it's easy to see that v sub x is just the difference between the rate of change of x2 and the rate of change of x1. In other words, the x component of the relative velocity is just the difference in the x components of the velocity vectors of particles 1 and 2. So, v sub x is equal to v sub x2 minus v sub x1. A similar relationship can be shown to be true for the y component, v sub y, and the z component, v sub z. In other words, the relative velocity vector is just equal to the velocity vector for particle 2, v sub 2, minus the velocity vector for particle 1, v sub 1. The relative speed, v, is just the magnitude of the relative velocity vector. As with any vector, the magnitude of the relative velocity vector is just the square root of the sum of the squares of its components. Suppose a particle is moving at 1 meter per second to the right, while another particle is moving to the left, also at 1 meter per second. Let's calculate the relative velocity and relative speed for the two-particle system. First, we need to define which particle is particle 1. Let's say particle 1 is the particle that is moving to the right, and we'll take this as the positive x direction. We can write the velocity vector for particle 1, v sub 1, by listing its components v sub x1, v sub y1, and v sub z1. The component along the x-axis, v sub x1, is plus 1 meter per second, and the other components are 0. For particle 2, the velocity vector component along the x-axis, v sub x2, is negative 1 since it's moving to the left, and the other components are 0. The relative velocity vector is just equal to vector v sub 2 minus vector v sub 1. The x component is v sub x2 minus v sub x1. Negative 1 minus positive 1 is equal to negative 2. In the same manner, we can calculate the y and z components. In this case, both are 0. So, what does this mean? If v sub x is negative 2 meters per second, it means that, to an observer on particle 1, particle 2 would appear to be moving to the left at 2 meters per second. Finally, it should be easy to see that the relative speed, which is the magnitude of the relative velocity, is 2 meters per second. Here's another example. Suppose particle 1 is moving at 1 meter per second due east, and particle 2 is moving, also at 1 meter per second, due south. Calculate the relative velocity and relative speed. This time, we'll draw arrows to visualize the vectors. Let's assume the positive x direction is due east and the positive y direction is due north. Here's vector v1, pointing east. Its components are plus 1, 0, and 0. So, the negative of vector v1 is pointing west. Here's vector v2, pointing south. Its components are 0, negative 1, and 0. And here's the relative velocity vector, which is the sum of vectors v2 and the negative of vector v1. We can calculate its components by subtracting the components of vector v1 from the components of vector v2. The components turn out to be negative 1, and 0. Note that we are putting the tail of vector v2 on the tip of negative vector v1 to add them. The vector sum is the arrow from the tail of negative v1 to the tip of vector v2. Finally, the relative speed is just the square of the sum of negative 1 squared and negative 1 squared, which turns out to be 1.41 meters per second. So, what does this mean? It means that, from an observer on particle 1, particle 2 appears to be moving away at 1.41 meters per second in the southwest direction. To calculate the relative or internal kinetic energy of a two-particle system, we need the reduced mass. The reduced mass, usually represented by lowercase Greek letter mu, is given by this expression. Mu is equal to the product of the two masses divided by the total mass. Here, m1 and m2 are the masses of the two particles. A good way to remember the formula for reduced mass is to understand why it is called the reduced mass. The answer is quite simple. The reduced mass is less than m1. It is also less than m2. Why is it less than m1? Let's rewrite the formula this way. We can see that m2 over m1 plus m2 is a number less than 1. So, we're multiplying m1 by a number less than 1. Obviously, the result is less than m1. Now, let's see why it is less than m2. Let's rewrite the formula this way. We can see that m1 over m1 plus m2 is a number less than 1. So, we're multiplying m2 by a number less than 1. Again, the result is less than m2. Let's look at a simple example. What is the reduced mass of two protons? The formula for reduced mass is m1 times m2 divided by total mass. Since both particles are protons, m1 and m2 are the same. We substitute the mass of a proton, shown here as m sub p, for both m1 and m2. It should be easy to show that the reduced mass is half the mass of a proton. In general, the reduced mass of two particles with the same mass is just half the mass of either particle. If you want the actual value here, you can look up the mass of a proton. It's 1.0073 atomic mass units, or 1.6726 times 10 to the negative 27 kilograms. Here's another example. What is the reduced mass of an electron and a proton? The reduced mass for particles with masses m1 and m2 is given by this formula. We just need to substitute the mass of electron, shown here as m sub e, and the mass of a proton, shown here as m sub p, for m1 and m2. To get the actual value, we look up and plug in the values for m sub e and m sub p. However, it's worth noting that we can get a very good approximation if we remember that a proton is almost 2,000 times more massive than an electron. This means the total mass in the denominator is approximately equal to just the mass of the proton. This gives us an expression where we can cancel the mass of the proton. This means that the reduced mass of an electron and a proton is essentially that of the electron. Note that the reduced mass must be less than the smaller mass. And when the larger mass is so much larger, as in this example, then the reduced mass is approximately equal to the smaller mass. For a two-particle system, the relative kinetic energy is 1/2 times mu v squared. Here, mu is the reduced mass and v is the relative speed. Here's a simple example. A two-particle system has a reduced mass of 0.5 kilogram and relative speed of 2 meters per second. Calculate the relative kinetic energy. Plugging the values for reduced mass and relative speed into our formula for relative kinetic energy, we get 1/2 times 0.5 kilogram times the square of 2 meters per second. The answer is 1 joule. Here's an example showing the two ways we could calculate the total kinetic energy of two particles. Suppose we have a 1 kilogram mass moving at 1 meter per second to the right, while another, also 1 kilogram, is moving at 1 meter per second to the left. You can apply what you learned in the previous examples to calculate the translational, relative, and total kinetic energies. Then, compare with the total energy obtained by adding the individual kinetic energies. Assume that particle 1 is moving to the right, and take that as the positive direction. This would be a good time to pause the video. Resume when you're ready to check your answer. Based on the given information, the total mass is 2 kilograms. The translational speed is 0. The particles are moving in opposite directions and have the same mass, so the center of mass should not be moving. Therefore, the translational kinetic energy is 0. The reduced mass is 0.5 kilogram. The relative speed is 2 meters per second. Using the reduced mass and the relative speed, we can calculate the relative kinetic energy to be 1 joule. The individual kinetic energies are both 0.5 joule, which add up to a total of 1 joule. The translational and relative kinetic energies also add up to 1 joule. Let us now take a look at the quantum mechanical description of a two-particle system. The Hamiltonian operator can be written as a sum of the kinetic energy operator for particle 1, which depends on the coordinates of particle 1, the kinetic energy operator for particle 2, which depends on the coordinates of particle 2, and the potential energy operator, which accounts for the interaction of particles 1 and 2. Here, we are using Q1 to collectively represent the 3 coordinates of particle 1, and Q2 to collectively represent the 3 coordinates of particle 2. This means that the wave functions depend on a total of 6 coordinates. Unless the particles do not interact, the potential energy operator depends on the coordinates of both particles. So, we say that the Hamiltonian is typically not separable, and solving the time-independent Schrödinger equation using this Hamiltonian operator will not be easy. Here's how we can make the Schrödinger equation easier to solve. We do a transformation of coordinates. We replace the coordinates of each particle, x1, y1, z1, and x2, y2, z2, by the center of mass coordinates, uppercase X, Y, Z, and the internal or relative coordinates, lowercase x, y, and z. The Hamiltonian operator then becomes separable. One term, shown here as t hat trans, depends only on the center of mass coordinates, while the remaining terms depend only on the relative coordinates. If we examine the expression for t hat trans, we can see that it is essentially a kinetic energy operator for a fictitious particle located at the center of mass, since the second derivatives in this expression are taken with respect to the center of mass coordinates. The mass of this fictitious particle is just the total mass of the two particles. Similarly, the second term is essentially a kinetic energy operator for a fictitious particle located at the coordinates x, y, z, in a coordinate system centered on particle 1. The mass of this fictitious particle is the reduced mass mu. The third term is the potential energy operator, which only depends on the relative coordinates. In fact, it only depends on the distance between the two particles. The distance between the two particles, given here by the symbol r, is the square root of the sum of the squares of the relative coordinates. This means relative coordinates are more conveniently expressed in spherical polar coordinates, r, theta, and phi. By switching to center of mass and relative coordinates, we can now find solutions to the Schrödinger equation that can be written as a function of the center of mass coordinates times a function of the relative or internal coordinates. These functions are obtained by solving two simpler differential equations. The total energy of the system is just the sum of the eigenvalues from these two differential equations. The differential equation for the part that depends only on the center of mass coordinates is essentially that of a particle in a box, which we have already explored in detail in an earlier lesson. In other words, by doing the transformation of coordinates, we have cut our problem in half since we already know the solution to this differential equation. Since this differential equation describes a fictitious particle located at the center of mass, with a mass equal to the total mass of the two particles, this differential equation essentially describes the translational motion of the two-particle system. The eigenvalue here is just the translational kinetic energy. From here on, we'll just call it translational energy. The differential equation for the part that depends only on the relative coordinates is what we need to solve. The solution depends on how the potential energy of interaction between the two particles depend on the distance between them. The eigenvalue here corresponds to the relative or internal energy, which includes both kinetic and potential energy. From now on, for brevity, when we write the time-independent Schrödinger equation for any system, we will assume that it refers to the differential equation for the relative motion. So, when you see h hat psi equals E times psi, h hat means the relative kinetic energy operator plus the potential energy operator, and E means the relative energy, and psi means just the factor that depends on the relative coordinates. The rigid rotor is a two-particle system for which the distance between the two particles is fixed. Therefore, the relative motion of the two particles can be described as rotation. No vibration is involved. Classically, the total energy is just equal to the translational kinetic energy plus the rotational energy. The classical rotational energy can be shown to be L squared over 2I, where L is the angular momentum, and I is the moment of inertia. The moment of inertia can be shown to be equal to mu times the square of the fixed distance between the particles. The quantum mechanical description of the relative motion is essentially that of a particle on a sphere, which we explored in depth in an earlier lesson. An important difference is that our particle in this case is one with a fictitious mass equal to the reduced mass. Otherwise, everything is pretty much the same. The wave functions are spherical harmonics. The quantum numbers are typically called J and M sub J instead of L and M sub L. The quantum number J is restricted to non-negative integers, and the quantum number M sub J is restricted to integers with absolute values less than or equal to J. The energies, the rotational energies, are quantized and are restricted to J times J plus 1 times B, where B is the rotational constant equal to h bar squared over 2I. The two-particle harmonic oscillator consists of two particles for which the potential energy depends on the distance between them according to this equation. The potential energy V is equal to 1/2 times K times the square of the difference between R and RE. Here, R is the distance between the particles, RE is called the equilibrium distance, and K is the force constant. If the system is confined to one dimension, then the relative motion is just vibration. The relative motion can be essentially described as that of a one-particle harmonic oscillator with a mass equal to the reduced mass of the two particles. The classical vibrational energy is 1/2 times K times A squared, where A is the amplitude of the oscillation. The amplitude of the oscillation is just the difference between the classical turning point and the equilibrium distance. The vibrational frequency, nu, is 1 over 2 pi times the square root of K over mu. In quantum mechanics, we find the energy is quantized. The allowed energies are V plus 1/2 times h nu, where the quantum number V is restricted to non-negative integers. The wave functions are the same as for the one-particle harmonic oscillator, but centered at equilibrium distance. In the next lesson, we will look at the quantum mechanical description of hydrogenic systems. These are two-particle systems consisting of a nucleus and an electron. Examples of hydrogenic systems include neutral hydrogen atoms and helium ions with a +1 charge.